Class, in today's video we'll be looking at the Moivre's theorem in complex numbers. So we have that if z is equal to r cis theta, which is the short form of is complex number in polar form, and n is a positive integer, then z raised to n will be equal to r raised to n cis n multiplying with theta. So this is the Moivre's theorem, of which we'll be applying in our activities of today. So let's look at the first example. So we have in this example, find this complex number and write the answer in standard form. So by the Moivre's theorem, which we've just checked, so with the Moivre's theorem, we said if z is raised to n, then this will be r raised to n cis theta. So in this case, we have this complex number raised to the exponent of 5. So we're saying 2 cis theta, cis theta, this has been raised to 5. So 2 is our r, and 30 degrees is our angle. So we'll have 2 raised to 5, then cis. So n will multiply theta. So our n is 5. So we'll have 5 multiplying with 30. So we can expand this. So 5 times 30 is of course 150. So we're having this. So now we can, in our question we were told to write the answer in standard form. So we need to convert this, our solution, into standard form, or regular rectangular form of complex numbers. So that is, we'll have 2 raised to 5 multiplying, so we're having cos 150 plus I sine 150. So 2 raised to 5, that is 32, and then cos 150 is from special angles, that is negative of square root of 3 over 2 plus I sine 150, this will be 1 over 2 I. Then we can multiply 32 throughout. 32 would divide with all the 2's that are denominators. So this will give us 2 into 32 is 16. So we'll have negative 16 square root of 3 plus 16i. And if you look at the expression, it's in standard form. So we're done. Let's look at another example. So we have this example we need to evaluate, and we're going to use the Moivre's theorem because of the exponent that we have here. So now, to simplify it, to simplify this one, we'll use the Moivre's theorem. So we'll say, so here our r is 2, our n is 8. So we'll have 2 raised to 8. Then we'll have cos, so we'll have 8 multiplying with 30 plus I sine 8 multiplying with 30. Then we can simplify it. 2 raised to 8 is 256, so we'll have 256. Then we'll multiply cos 8 by 30, which is, so we're having 8 by 30, which is 240, so we'll have cos 240 plus I sine 240. Then we can simplify these two. So cos 240 will give us negative 0.5. So from the special angles, that is -half plus I. Then sine 240. Then sine 240 gives us negative square root of 3/2. Okay, then we can multiply through with 256. So we'll have 2 divided into 256. Then 2 into 256 is 128. So which means here we'll have negative 128. Sorry, this is minus 128I square root of 3. And this is our final solution. Let's do another example. So we have this other example. So if you can check it, it's already in standard form. So first we need to convert it into polar form, then we can apply the Moivre's theorem. We have R. Our R will be equal to, this is 1 squared plus 1 squared, which is just equal to square root of 2. Then our angle, reference angle alpha, equal to tan inverse of y over x, which is y is 1 and x is 1. So we're having 45 degrees. So since if you are to graph this complex number, it's all lying in the first quadrant. So which means our angle is just 45 degrees. So writing it in polar form, it will be, we'll have 1 plus I raised to 8. This will be equal to, so our R is square root of 2, so we have square root of 2 over 45 degrees. Then this whole thing is under 8. So now applying the Moivre's theorem, we'll have R raised to 8. So R is square root of 2. So we're having, so we can put it as 2 raised to half and 8 there, multiplying. So cos 8 by 45 plus I sine 8 by 45, like that. So 2 into 8 is 4, so 2 raised to 4 is 16. So we have 16 here. Then we have 45 by 8, giving us 360. So we're having cos 360 plus I sine 360. Cos 360 is 1, sine 360 is 0. So we'll have 16, then we'll have 1 plus 0I. Then if you multiply 16 throughout, we just have 16. And this is in standard form, and it's our solution. So we'll take it further now using the Moivre's theorem for finding roots. So where if Z is equal to R CIS theta and it's a complex number, then there exists n distinct nth roots of Z given by this. So we'll have W of K will be equal to R of 1 over n CIS of theta plus 360 multiplying with K over n, for K being equal to 0, 1, 2, and n minus 1 for n greater than or equal to 1. So we'll be using this principle for finding the roots of a complex number. Let's have our first example. So in this example, we're saying find the cube roots of 27. So if we're going to apply the Moivre's theorem for finding roots, we're first going to convert the 27 into trigonometric form. As it is in standard form or rectangular form. So writing this in polar form, remember this expression can be viewed as 27 plus 0i. So finding our r of x squared plus y squared is as 27 squared plus 0 squared. So this is just the same as 27 square and the square root. So which means the square root will cancel with the square, leaving us with r being just 27. And our angle here is 0. Our angle is 0 due to, if we were to say we find the inverse of, remember we're having 0 over 27. So which means tan inverse of 0 is just 0. So our angle is just 0 degrees. So writing this in trigonometric or polar form will result it into be 27 CIS 0 degrees. So that's it. Then applying the formula of finding the nth root, and in this case we're looking for the cube roots. That's up to 3. So 1 over 3. So we found 27. So which is this. So now we'll use the formula for finding the nth for the roots. So we'll use this formula to get the cube roots of our expression. So that is, we'll write the way the formula was equal to. So in this case, r is 27. Then the n in this case. So cube root, we're talking about this. So we're having 1 over 3 here. N is 3. And then, so we have 0 degrees since our theta is 0. So 0 degrees plus 360 degrees k over our n is 3. So which is 3. Then for k, in this case k, we are going to have values of 0, 1, 2. Remember, the maximum is always n minus 1. So our n is 3. So 3 minus 1 is 2. So for these values. Now, so we're going to substitute for each k value. So let's start. So let's say for k is equal to 0. Our angle, just the angle, our angle will be 0 degrees plus 360 0 over 3. So here our angle basically will just be 0. So now replacing it now in our formula, so we just pick this part. We just pick this part to get the angle. So now replacing the whole angle in our expression, we'll have, so W of, so our K for this one is 0. It's equal to, so 27, 1 over 3, then CIS of 0 degrees. So if we were to replace 0 in the, let's say we write it in its full form to be 27, 1 over 3. We're having cos 0 degrees plus I sine 0 degrees. The cube root of 27 is 3. Then cos 0 is 1. Plus sine 0 is 0. So we're having 0 there. So 0i. So our answer here is just 3. We progress. We go for k is equal to 1. For k is equal to 1. Okay, so just solving the angle. So have our theta is 0. So we're having 0 plus 360 applied with 1 over over 3. So this will give us 360 dividing by 3, which is 120. So our angle is 120 degrees. Now replacing it in the whole formula, we'll have our k is 1, so k of 1 is equal to, so our r is 27, 1 over 3, CIS of 120. So this is cube root is 3. So having cos 120 plus I sine 120. So cos 120 is 1 over 2, which is negative, so it's negative 1 over 2, plus sine 120 is square root of 3 over 2, and this is I. Simplifying it further, we multiply 3 throughout, we have negative 3 over 2 plus 3I square root of 3 over 2. And it's in standard form, it's complete. So the last one is for when k is equal to 2. So when k is equal to 2, finding our angle, so we have 0 degrees plus 360, 2 like that, over 3. So 360 by 2 divided by 3 will give us 240. So our angle here will be 240 degrees. So replacing the angle in our formula, so we're saying of 2 will be equal to, so 27, then CIS of 240. So this gives us 3. Writing it in complete form will be cos 240 plus I sine 240. So cos 240 is negative 1 over 2. So have negative 1 over 2. Then sine 240 is negative root 3 over 2. So have negative I root 3 over 2. Like that. Then simplifying it, we'll have negative 3 over 2 minus 3I square root of 3 over 2. And we found the cube roots, the 3 cube roots of 27. So our cube roots are, so we had, the first one is 3. That's the first one we found. The second one was negative 3 over 2 plus 3 root 3 over 2I. And the last one is negative 3 over 2 minus 3I square root of 3 over 2. Like that. So that's how you find the nth roots using the Moivre's theorem. Let's look at another example for further understanding. So in our next example, we are finding the fifth roots of z is equal to 1 plus I root 3. So feel free to pause the video and then you can confirm the answer. Okay, so we first need to convert into trigonometric form. So in this case, our r is equal to, we'll have x squared plus y squared, that's 1 squared plus square root of 3 square, then we have a square root. So this will give us 2. Then for our angle, we're saying theta is equal to tan inverse of root 3 over 1. So if you check we're having both the real part is positive and the imaginary is positive, so it's in the first quadrant, and tan inverse of root 3 over 1 is 60 degrees, so it's just the same angle. So writing it in trigonometric form, it will be z is equal to 2 of 60 degrees. So we're now going to look for the fifth roots of this expression. So we said our limit is for n minus 1. So for this one, k will be equal to 0, 1, 2, 3, up to 4. 5 minus 1 is 4. So these are the fifth roots. There are 5 of them. So we're replacing them in the formula. Remember the formula, this one. Okay, so we're replacing them in this formula. So since we're saying our fifth root, so our n is 5. So let's start. So we'll start with the one for, say, k is equal to 0. For k is equal to 0. So we replace wherever there is a k in the expression, we replace with 0. So that will be, so I want to split it like last time. I'll just do the whole thing at a go. So that is, we'll have of 0 is equal to r, our r we say it is 2. So we'll have 2. So 1 over 5. So our theta is 60 plus, so 360 in this case is now multiplying with 0 over 5. Then we simplify it. So this one is 2 raised to 5. Then, so we're having 360 by 0 will be 0. So we'll have 60 dividing with 5, which is 12. So we'll have 12 here. Then now we can simplify it. So we can just simplify it by writing the root of the cube root, the fifth root of 2, which is, we'll write it maybe in that format, then 5 there, then CIS of 12. Yeah, so this is the first root we found. Then we can also now look for the other one. So for k is equal to 1. So replacing in the formula, so we'll have W of 1 is equal to 2 raised to 1 over 5. So CIS of 60, our angle is 60 plus 360 multiplying with 1 over 5. So we're simplifying this already, so this will be 2 raised to 5. Then we have CIS. So 60 plus 360 will give us so if we add 60 plus 360 and we divide by 5, we'll have 84. Yes, 84. So this will be 84. And this is the second root. Going further, k is equal to 2. So we change the narrative again. So have of 2 is equal to 2, 1 over 5. And CIS of 60 plus 360 multiplying with 2 over 5. Then simplifying this expression, so here we are having the fifth root of 2 and CIS. So 360 by 2, 720 plus 60, 680, dividing by 5 will give us 156. So this will be 156. So these will just leave them here, since if we try to find the cosine sine, to be difficult to deal with them since they're not special angles. So this is the case here. We proceed to the third root. So for this one, it's k equal to 3. So we'll have w of 3 will be equal to 2 raised to 1 over 5. CIS of 60 plus 360 multiplying with 3 over 2. So the fifth root here, CIS, then we can simplify this. So 360 by 3 will give us 1080 plus 60 will give us 1140. Then dividing, so this should be 5. We're dividing by n, which is 5. So our n is 5. So dividing by 5 will give us 228. So this will be 228 like that degrees. So this is our third root. And then we find, this is not our third root, it's our fourth root, sorry. So now our fifth root will be for this one, we're applying k is equal to 4, which is the last one. This is our fifth root now. So for the value of k is equal to 4, so we'll have 2 raised to 1 over 5. CIS, so we're having 60 plus 360 multiplying with 4 over 5. So this is the fifth root of 2. Then CIS, so 360 by 4 will give us 1440 plus 60 will have 1500. Divide by 5 will have 300. We have 300 like that. So these we have found are the fifth root. So this one here. So there should be 5 in total. So we found these. And basically that's how you find the roots of a complex number using the Moivre's theorem.